Welcome to this presentation, Learn CircuitPython using the Adafruit Trinket M0. I'm Altbier and I'm going to walk you through this presentation. So what is CircuitPython? CircuitPython is a programming language that is used to code low-cost microcontrollers. So these are hardware development boards usually that interface with other hardware like LEDs and things like that. And if you think about other hardware development platforms like the Arduino, they use a scripting language of their own, and CircuitPython uses Python. It's based on the Python programming language. They've made it to where it's easier to code and see your results right away, since all you have to do is copy files to a USB drive instead of having to push code to the board. It'll auto-recognize when files change and reload the code when that happens, and it makes it a very easy way to program hardware development boards. So what is the Adafruit Trinket M0? This is a microcontroller board, a hardware development board that was developed by Adafruit, and it can work with both CircuitPython and Arduino. So you can load firmware on it that will let it work with the Arduino IDE. But by default, it comes with the CircuitPython firmware installed. So when you plug it in, what's going to happen is it's going to open up a USB drive on your machine. And that USB drive, it's a very small drive that has some files, including like a demo program that has a main PY file running it. All you would have to do to change that code is edit the main PY file with your own Python code. You don't require any kind of integrated development environment or anything special to work with it. You're just either copying files to that drive or editing the files that are on that drive directly. This board has, this is a small board, so it has only 5 GPIO pins, but each one of them has a lot of different functionality built into it, so it's very powerful. And it has 256K of flash, 32K of RAM, and it's running an Atmel processor that's a 32-bit processor. So it's a powerful little board and very fun to play with, and that's what we're going to walk through here today. So Adafruit and CircuitPython resources. The Adafruit website is adafruit.com. That's where you're going to find documentation and resources for all of the products that they make. Specifically, the Trinket M0 is their product 3500. So if you go to adafruit.com/product/3500, that'll bring you to the Trinket page where you can actually purchase a Trinket there or link to the other documentation. Like this second link is on that first page. So you don't have to worry about typing all of this, but this is all of the documentation for the Trinket is available via that site. CircuitPython has its own website, circuitpython.org, and it's a great resource for the documentation and software and example code. So this is where we'll go to get library files that we'll need to do certain things with the CircuitPython code on the Trinket. They also have a software editor that has a built-in serial monitor, and we'll talk about that in a minute. So Electronics 101. We are not going to teach Electronics 101 here, but that is knowledge that is good to have if you're working with hardware development platforms. I do have a separate presentation on that under altbier.us/electronics. So if you're interested, you can walk through that presentation and get your basic electronics knowledge up that will help you when working with the hardware development platforms like the Trinket and CircuitPython. The Moo editor software. So this is an integrated, while an integrated development environment is not required to work with CircuitPython, this is a simple code editor that lets you work with the Adafruit CircuitPython boards. So it will recognize when a board is plugged in, and it will be able to load code directly from the drive, the CircuitPy drive that it mounts, and it also has a serial monitor in it, so you can get immediate feedback from what your board's doing and see what it's doing. So you can download it at codewith.mu. And if you're using this, the first time that you start it, you'll be prompted to select a mode. It supports several different modes, and you'll want to select the Adafruit CircuitPython mode. And then if you try to launch Mu when a board is not connected, it will give you an error saying that the board's not connected. It'll still let you launch and write code, but it won't be able to interface with the board. Even if you plug it in later, I've noticed it has trouble recognizing it. You have to relaunch it. But once you're plugged in and ready to go, you'll get a nice window to start modifying code. So serial monitor, we talked about that a couple times already. To view the serial output that your board, the Trinket in this case, is going to be sending, you need a serial monitor. That's something that's going to be looking for those serial signals coming off the board. Now, usually what happens is when you plug in the USB device, it's going to set up a device driver, including a serial interface if that's something that the board supports, which most hardware development boards do. In the Mu editor, there's a built-in serial monitor, so all you have to do is click the button that says serial, and it'll open up the serial monitor, and you can see what's going on. But you don't have to do that. You can just identify which COM port on your machine, the USB COM port that your device is using. And you can do that by opening up your device manager, which is going to be different based on your operating system. Once you've identified the COM port number, then you just need to open up a terminal program that supports serial connections. PuTTY is one example, but there's others out there. And you're going to configure it to connect to that COM port with a baud rate of 9600 baud. And once you open that up, you'll see all the output that's being sent by your board. Now let's talk about connecting the Trinket. So connecting the Trinket, when you first connect it up, it's going to open up a small USB drive that's named CircuitPy. And this drive is going to be where you place all of your code and library files. It comes installed usually with a main PY file and some library files in a lib directory, and this is demo code that it's using that's going to like cycle the colors on the dot star LED. This is an RGB LED that's on the board. If you can see this off to the left side of the screen, there is a Trinket that's running the demo code now. So you want to verify the Trinket firmware version, because there's several different versions of CircuitPython, and the compiled external library files that we're going to be using to add for different projects are version dependent because they are compiled. So if you have a board that's at version 2 dot something and you have the library files for version 3 dot something, they're not going to be compatible. It's going to give you errors. So you want to make sure that you know what version of CircuitPython your board is running. And the way you do that is on the CircuitPy drive, there's going to be a file there named boot_out.txt. And that file is going to tell you what version of code is running. This is a file that gets created every time you boot up the Trinket, and it's going to tell you what version of CircuitPython it's currently running. So you can use that to make decisions about whether to upgrade or whether to download the library files for that version. So upgrading the Trinket firmware. This is a fairly easy process. Basically, you're going to download the firmware file from CircuitPython.org. They have firmware files there for a bunch of different boards, so we want to make sure we add on there /board/Trinket_M0. That's going to pull up the page with the firmware files for our specific board that we're going to be working with today. If you click on the Download UF2 Now button, it's going to download the latest stable firmware version. There's also other links there to download different versions. The latest stable version at the time that I'm recording this is version 5.3.1, and that's what we're going to use in these labs. So if you connect the Trinket, it'll open up that CircuitPy drive, and from there you can actually choose to back up the files that are on it to your PC before you do anything, because there is a chance those files are going to get deleted when we do the firmware upgrade. So if you want to save those files like code or anything that's on there, it's a good idea to back it up. We're going to click the reset button on the Trinket twice, and we're going to do this not like a mouse double click, but more like a click, pause, click. And then that's going to make the dot star LED in the middle turn green, and then a new disk drive is going to appear called Trinket Boot. The CircuitPy disk drive will disappear, and the Trinket Boot disk drive will open. In that Trinket Boot drive, we're going to copy the UF2 firmware file that we downloaded over to that drive. And that's all there is to it. As soon as the copy is done, it's going to recognize that there's a new firmware on the drive. The red LED is going to flash, and the Trinket boot drive is going to disappear. And then it takes a little while for it to get the new firmware running. So maybe 30 to 60 seconds later, you're going to see the CircuitPy drive reappear. Now, in this process, especially if you're going between major versions, like between version 3 and version 5, the main PY file and the library files that are in the lib directory may get deleted. In fact, usually they do. If they don't, they're not going to be functional because the compiled libraries are not going to be compatible. And that's it. Your Trinket's running the new firmware. And before I move on, I am going to do that because one thing that I noted earlier is that my Trinket and most of the people that are in the BSides hardware hacking village working with that kit, your Trinket is at version 3.1.1, and we're going to want to upgrade it to version 5.3.1. So I'm going to show you how to do that right now. So the first thing we want to do is make sure that we have our Trinket plugged in, and we do. And then we're going to make sure that we have the CircuitPy drive, which is right here. And it has, as you can see, some test code on there, a main PY file, there's a lib directory, there's other stuff on there that we're less worried about, like the Windows 7 driver. Then we have our UTF file, which we've downloaded. And that is right here. So this is the Adafruit CircuitPython Trinket M0 EN for English US 531.uf2. So that UF2 file is what we're going to want to copy over to the Trinket boot drive, but we have the CircuitPy drive up. So what I'm going to do right now is click, pause, click. And you'll see that Trinket boot drive has replaced the CircuitPy drive. And so now we have the current UTF file, or UFT file, I keep mispronouncing that, is on here. And it has some information about it, but we don't care about any of that. We just want to copy this file over to it. So let's copy Adafruit, no, not that one. And my drive letter is E, so I'm just going to go to E. And when that's done copying, the Trinket boot drive disappears. And a couple seconds later, that was actually quicker than I've seen it happen, the CircuitPy drive opens. And so now if we were to look at our boot out, it's going to show 5.3.1, which I'm not sharing my notepad. But yeah, it's at 5.3.1 now. But one thing you'll notice is that there's no main.py here file now. The main py is gone, And if I look in the lib directory, it's empty where there were files in there before. So in the process of upgrading, it did nuke my my files, and that's fine because we're going to put it back with new files on there. So that's not a problem. All right, let's get back to our presentation. So talking about library files, whether you recently upgraded like I just did, or you just want to create a new project with your current version of CircuitPython, you're going to want to download the library files to your PC. There's such a small amount of storage available on the device, the Trinket, we can't copy all the library files there. We're going to have to be very selective about which library files we put on there. And and it's a good idea to have them all available so that as you're working projects, you're not then having to stop and say, oh, I need this file, I need that file. You'll have them all in a directory that you can just copy over what you need. These are compiled library files, so they are version dependent, like we said. But they come in a bundle package that has all of the library files for a given major version, like 2 or 3 or 5 or 6 or whatever we're doing. So we want, in my case, to get the bundle for the 5 code because we're running 5.3.1 now. And I should mention that there are a number of libraries that are built into CircuitPython that do not require an external library file at all. So the only time you're going to need to download library files are when you're using a service that's not already got a library inside of the CircuitPython firmware. So where do we download this from? If you go to circuitpython.org/libraries, you can choose the bundle that corresponds with your version and extract it. It comes as a zip file. And then once you're in that, you can download any of those library files from the lib directory where they're all at over to your CircuitPy lib directory. There's also a lot of good examples here. They have examples on how to do different things with CircuitPython, and it is updated to be version compliant so that all the examples in the 5. Bundle will work on 5. Code. So testing after a firmware upgrade. So to test, when you upgrade the firmware, you're going to want to test some code. So you're going to see that it's going to delete the files usually, but if it doesn't delete the files that are in place are probably not functional, and it's probably got an error that it's thrown you. So it's best just to clear out any .py files that are on the drive, the CircuitPy drive, and to delete all the library files that are in the lib directory. Basically, you can delete everything off that CircuitPy drive with the exception of a couple of empty files and a directory that are there for the sole purpose of preventing a PC from storing hidden files on the drive. So this .meta data never index, .trashes, those are examples. The FS event, that is got a no log file at 0 bytes. These are all 0 byte files with the exception of the directory, which is holding a 0 byte file. And all they do is signal the operating system, and this is set up for various operating systems, not to store things like a trash bin or some index file, something like that on the drive, because this drive is so small, even just the few kilobytes of storage that might take is going to impact us. So we want to make sure to keep these 0 byte files there. That way we make sure that we don't add anything hidden to our CircuitPy drive when it's mounted. Other than that, you can nuke everything else off of there. You can leave the lib directory as long as it's empty, or you can nuke it and add it when you need it. That shouldn't be a problem. So then the first thing you're going to do with no files on there is just run a quick test program. So the test program that I have here is fairly simple. It doesn't require the drive or the Trinket to be connected to anything. It's just going to blink the onboard red LED that's in the corner of the Trinket. and it's going to print some text to the serial output. And that's all it does. So what we want to do is load this up into a file called main.py that's on our Trinket. And so let us do that real quick. Okay, I'm going to launch the move program to show you how that's going to work. And then I'm going to, right now it has an untitled file. Normally if there's a main.py file on the board, it will grab that and load it and display it for you. But since that doesn't exist, it just started with an empty file. So what I'm going to do is load up my quick test code from another editor and paste it here. And then we're going to save this. And we're going to be given a chance to name it, and that's where I'm going to call it main.py. And you'll see it opened up the CircuitPy drive. And so when I save that, let me show you, it automatically launched it, and you should be able to see on the left, or the top left part of the screen, the red LED is now blinking. Now I'm going to open up the serial monitor on the move program, and we can see that it's displaying my little hello CircuitPython from the code. And it does that every time it loops through here, which, being that I have 2 pauses for 1 second each, that's about every 2 seconds it's going to print that out. And that means it's working. You'll notice also that the center light, that RGB LED light, is solid green. That indicates that it is currently running code. That LED provides a number of different status messages to show if you're running code or if there's some type of error with the code, what that error could be. So we will leave that be, and we will move on to our presentation. So that tested good. And here are those status codes that I was telling you about. So the Trinket and its CircuitPython firmware is going to attempt to help you troubleshoot your problems. So the RGB LED that's on board is called a dot star LED. That will display a status color, and it'll flash an error code if there's an error. So I have a chart here on the right that shows steady green means it's running the code. If it was pulsing green, it would mean that the code finished running and didn't have a loop to continue, or there was no code on the board for it to run. A steady yellow or a pulsing yellow are indications of a safe mode or a crash. White and blue typically happen as it's booting up for the first time. You'll see white and blue flash before it goes to green. Now, in the case of an error, it's going to try to tell you what type of error it is. So what you'll see is it'll display certain colors in a flashing pattern. And the first color that gets flashed will tell you what type of an error it is, whether it's an indentation error or a syntax error, some value error. And then usually the flashes that follow that first color indicate what line number in the code that the error appears on. So that if you don't have access to a serial monitor, you can use these flashing colors on the board to determine where the problem is in your code, which line is throwing the error. It's a very helpful thing to have if you're wanting to quickly troubleshoot some simple code. But if you have a complex piece of code, the serial monitor is going to be more help than this. All right, so integrating circuits with the Trinket. So far, we haven't connected our Trinket to anything. To have it control external circuits, we must integrate it into those circuits. That means connect it up. So in order to connect it up, we need to know how can we connect it up. So we need to look at what pins are on the Trinket that we can connect external devices to. So it has internal pins, as we discussed, for the red LED that I'm flashing, or the RGB LED that's in the center of the board. Those have internal pins that we can address and program. But there's external pins as well. So there's 5 general purpose input-output pins, GPIO pins, that are labeled 0 through 4. And each of those have different features that should be considered when you're looking at using it for a part of your circuit. Some of them are digital only. There's one of them that's true analog. The ones that are digital have PWM, that's pulse width modulation. There are a touch sensor, capacitive touch sensors built into 3 of the pins, etc. There's also pins on there that include voltage input. There's a couple of voltage outputs. There's a ground. There's a reset. There's pins that do those functions or provide those services in addition to the GPIO. The pinout for the Trinket, which is available in the Trinket documentation, and I've cut a snapshot of it for this slide deck. This shows you a lot of information about each pin that tells you what that pin is capable of. So you'll notice that the pink touch label is on these 3 pins only. That means if I'm going to use capacitive touch, it has to be on one of those 3 pins. You'll notice that the wavy line, according to this chart, this key, means this is PWM. That means these are using pulse width modulation. Now, the pin 1 here has a little analog symbol line next to it, because this pin is the true analog out. That NN, so we can do analog in or out on this pin, and it is indicated with the DAC. So we can tell the different functions of the different pins by this chart, and some of them do things with using it for interfacing with other boards, like it supports I2C and some other protocols on different pins. That's why some have a little RX and a TX listed. So basically what you're going to do with your circuit will determine which pins you want to use on the Trinket to do that with. All right, so working with CircuitPython on the Trinket. So CircuitPython is based on Python 3. So most things that work with Python 3 are going to work with CircuitPython. There are some things that don't, but I'm not going to compile an exhaustive list here. You'll find out what works and what doesn't, usually by trial and error, and most things are going to work. CircuitPython libraries, as we talked earlier, are separate files that are either separate files that are compiled and put on the lib directory, or there's something that's built into CircuitPython, and they're separate pieces of code that are dedicated to a certain thing. So when you're wanting to work with the dot star LED, for example, we have to load a dot star library to get it all the definitions and the pieces of code that are specific to that piece of hardware. So you'll be dealing with libraries often in code as you call different library files, whether they're internal or external, to work with your code. Now the CircuitPython code is usually just put in a file or files on the root directory of that CircuitPy directory. And it can be more than just the main PY that I used in an example. It actually looks for 4 different names. It'll look for code.txt, code.py, main.txt, and main.py in that order. And then the first one that it finds out of those 4, it's going to open that up and run it. I'm using main.py just because that's what I'm used to. I know some people prefer the code.py, but there's really no rhyme or reason why you would use one over the other. Just use what is comfortable for yourself. Any editor will work to modify your code. We already talked about that. when you are done writing to a file on the CircuitPy directory, whether that's you have the file open in an editor and you write to save your changes, or if you copy a file over to replace one that's there, as soon as the write or the copy is done, the file immediately gets run on the board again, because it's going to be looking for changes, and when it sees a change, it resets with the new code. Python quick reference. I decided to include this slide here, even though I'm not going to spend much time on it. For those that need a quick reference and don't want to dig through documentation as they're working with this project, I thought this could be handy. This goes into the Python 3 quick reference charts. It includes things like how to do imports and container types and conditional loops and iterative loops, and it gives you all the syntax stuff. So if you're someone like me who works with a lot of different languages, just that quick look at, oh yeah, that's how we do it in Python again, that's always handy. So I thought I would include this, even though I'm not going to speak in great detail to it here. And now we get to the projects. So for the CircuitPython Trinket projects, we're going to be working with 2 different physical circuit layouts, and then I have 4 pieces of code that we're going to walk through that work with that hardware layout. And these are broken up into 2 different labs, so Lab 4 and Lab 5, which are part of the DFW Hardware Hacking Village. So there will be separate videos detailing out Lab 4 and Lab 5 in a lot more detail than what I'm going to present here. I am going to walk through these labs here, but if you want more detail on the hardware or the code that's going to be presented in this next section, please visit the YouTube site and select Lab 4 or Lab 5, and there'll be separate videos for that. So our first Lab 4, is for Adafruit Trinket LED control. So basically we're going to have the Trinket control an LED. And we're going to use a button and regular Trinket controls to make this work. So this is the circuit that we're doing, and the LED is a fairly typical circuit design. We're coming off of a digital pin D4. We're going to have a 100 ohm resistor going to a standard 5mm LED, and then it's going to go to ground. Now, unlike my previous schematics that I used in some of the other classes, like the Arduino class, I'm not drawing the lines all the way to reconnect to everything. Instead, I'm using these labels, which show that they're all interconnected. I think it makes it easier to read, and when I do schematics for my projects, not for training, I typically use labels. So I wanted to introduce that here. So we have ground here is going to the ground pin. So that's our LED. Now we also have a button that we're going to read from. It's a tactile switch. So that tactile switch has 2 sides to it. It's an SPST switch, so single pole, single throw. It might have 4 pins, but it's still just single position, single throw. And what we're going to do is wire this into D3, where we're going to be looking as an input for some voltage. And then on the other side of the switch, we're going to wire that voltage, 3.3 volts. So we're going to wire it to the 3.3 volt pin. And then we're also going to, on D3, in addition to the button, we're going to hook up a 10K ohm resistor and bring that to ground. Now, the whole reason for this 10K ohm resistor, this is a pull-down resistor, and it's just going to make sure that D3 is always at a low state, meaning low voltage, unless we push the button and it gets this 3 volts. So this makes sure that we don't, if we didn't bring this to ground with a resistor, we could have some signals seen there as if it was high voltage, even though we're not pushing the button. It's just to avoid that happening. So it's a fairly simple circuit. And here's what it looks like. So the physical layout, you can do it on a breadboard, and I did as part of designing this class. But then for this lab, we're going to use the custom strip board that was provided to the BSides attendees in the kit. And we're going to connect up the LED and the button to the Trinket. Now, one thing to note is that we are using what's called the VCC rail. It's one of the power rails. It's the negative power rail. And I did this just to make it look cleaner so that you can see what's going on a little bit easier. And the strip board connections are all detailed off to the right here, so you can see where exactly which holes to plug the things in, and the strip board labels with letters on the bottom and numbers on the side so that you can identify which holes I plugged what thing in. Now let's get to the code. So the first piece of code that we're going to look at is that test code that I loaded onto my Trinket when I did the firmware upgrade. So we're just going to step through that real quick. So we have our first 3 lines are loading libraries. All 3 of these libraries are built into CircuitPython, so we don't need to have any external files on the CircuitPy drive. So we're importing board, which has all of the actual board pin assignments on it. We're going to load digital I/O and time. So line 5, we're assigning an object called RLED, and we're assigning it to a function in the digital I/O library called digital in/out. And then we're going to tell it to use the pin board.D13. And D13 is the pin number associated, if you were to look at that pinout diagram, that's the pin number associated with the internal red LED that's on board. So now, because this is a pin that can do inputs and outputs, we have to tell it what direction we're going to be sending or receiving signals from. So we tell it RLED.direction is equal to the digital I/O direction output. So we're telling it this is an output pin. I'm going to send signal out, voltage out. Line 9, it starts a while true loop, which is going to run indefinitely. This is our main loop. Line 11, we have our print to serial. That's what prints out to the serial output. On line 13 is where we set the RLED.value. This is the value that that object is going to store. We're setting that to true. Now, because this is a digital output, the only options I have to send it are binary. I could send it true, false, or a 0 or a 1. It's not going to take anything else. It'll error out if you try to give it something else. So I'm giving it true, and that's going to turn the LED on. And then I'm going to pause for 1 second. That's the time sleep function pauses it for 1 second, so it shows it on for a second. And then I'm going to set it to false, and then the last line sleeps for a second, and then it's going to repeat through this loop. And that is all that this code does. It's very simplistic, just blinks an LED and prints a line of text to the serial. Okay, let's move on to the next piece of code. So this one is very similar to the last piece of code in that we're blinking LEDs, but now I'm going to blink both the internal red LED along with the external LED that we wired into our circuit. So we do the same imports and we do the same LED assignments. So we have the pins listed. D13 is the red LED, and then D4 is the pin that we wired our external LED for, and I called it LED4 simply because that's the name that was on the schematic. I set them both as output pins, and then we start our main loop, and then I'm going to set their values to true, which I'm doing this all in one line. You can set the red LED value equal to the LED value or LED4 value equal to true. So this makes it all equal to true. Then I print to serial, and I'm going to print both the red LED and the LED4 values. I'm going to sleep for a second, And then I'm going to do the same thing to turn them off. I'm going to set them both to false, I'm going to print again, and I'm going to sleep. So it works very similar to the other code, but now we're dealing with an external LED. So our next piece of code is to fade an LED using pulse width modulation. So where in the previous code we defined a digital output pin for our LED, in this code we're going to define a PWM, which stands for pulse width modulation output pin. This is going to mimic an analog signal, allowing the LED to be at states that seem to be in between on and off. So let's walk through what's different here. So instead of the digital I/O, I'm going to use the library pulse I/O. And then we're going to assign the LED4 object to a pulse I/O object called PWM out. And we're going to give it the D4 as the pin again. Now, because this is an output only object, we don't have to specify that it's an input or an output like we did with the digital pin. This is only output, so we don't need to do that. So then what we're going to do next is start a for loop, actually a couple of them, a for loop that's going to bring the LED from 0% on, or off rather, up to 100% on. And then a second for loop is going to bring it from 100% on down to 0. And we're going to do this with what's called a duty cycle. The way that pulse width modulation works is it actually will pulse the signal between on and off a number of times very quickly. And that amount of time that it's on is going to be the brightness that we see, or the percentage of output that the LED is going to show. Now, the duty cycle is made up of a 16-bit number. So it starts at 0, which would be fully off, and it goes all the way to 65535, which is fully on. That would mean 100% of the time it's keeping high voltage. Now, if it was half that, let's say it's 32,000, that means that half the time, 50% of the time, it would be pulsing high signals, and the other 50% it would be pulsing low signals, high being the full voltage, low being no voltage. So it's not really an analog signal, it's just mimicking one. And so what we're going to do is use that duty cycle. So our for loops are going to loop through an integer range. So this range is how we specify how many iterations of the for loop that we want to do, right? And we specify a variable I when we're using the for loop, so that I will be our iteration of the loop. It'll count it either up or down. So in this first for loop, we're counting up. So then I'm going to set my LED4 duty cycle to be equal to, and then here I'm doing a little bit of math. I'm taking I, which is my iteration number, dividing it by 100, which will move the decimal place over 2 times. Then I'm going to multiply that by 65535. Now, to make that simple, let's say I was 50. We're at 50%, right? So that means I divided by 100 is going to be 0.5, right? Because it's 50 and we move the decimal place, and now it's 0.5. So now 0.5 times 65535 is going to be 32,000 some odd. It's half of what that number is. And it's going to do that all the way through. So it's going to take that 65535 and we're dividing it out as a percentage of 100. So whatever percent we're at with I, it's going to turn the duty cycle up to that percentage of on. Then we're going to do a serial output to print off what my current duty cycle value is. We're going to pause. Now our pause here is going to be very small because we're going through 100 different values here, and then we're going to go through 100 more. So we're not going to pause for a full second. We're going to pause for 100th of a second, and then it's going to run very fast through here. And then we're doing the same thing in reverse here. Now the way we reverse it is using the range. We have these extra settings, the -1, -1. And basically that's telling it to count down backwards. So it's going to start at 100 and work its way back. And we do the same exact math on the duty cycle and print the same way and pause the same way. And that's going to produce a nice fade effect as they fade the LED on and off. Let's look at our next code. So we have turning LEDs on and off with a tactile switch. So for this code, what we're going to do is go back to using the digital I/O library, and we're putting in an extra item. So we have our red LED, we have LED 4, just like the previous examples, but now we have SW1. This is our switch. And we're assigning it a digital I/O pin just like we did the LEDs, but on the direction, switch 1's direction is going to be an input. And then in our main loop, we're going to set a variable called button that we're going to make equal to the switch 1 value. So that reads in the current value of switch 1, whether it's on or off. So that value, being that this is a digital input, is going to be a 1 or a 0, a true or false. That's the only value it can produce for us. So button will either be true or false. So now I'm going to print out what that button value is to serial. I'm going to use a conditional, an if statement that says if that button value is equal to true, then I'm going to light up my LED by setting the red LED value to true. Now I'm just playing with the red one at this point because I want to show a different way to do this for the other one. And then else means that condition is not true, which means it's false. Then I'm going to set red LED to false. Well, another way we can do this, a much easier way, knowing that the switch value is either true or false, is just to set it to the LED value. So I'm taking that in the next line, LED 4, I'm going to set its value to be equal to button, and button is going to be a true false. So when I push the button, it'll light up. When I release it, it will release. So with this code, and I sleep for like 0.2 of a second. So it runs through fairly quickly. That way I can tell pretty instantly when I get button pushes. But yeah, with both of these ways of doing it, it's still going to light both LEDs at the same time, and it's still going to turn them off at the same time. I just wanted to display the two different methods of working with an input to control a device. All right, so now we're on to our next lab, Lab 5. And here is the schematic for Lab 5. It's very simplistic. Basically, we have our 100 ohm resistor that's being connected to pin D2. We're going to connect a standard 5mm LED to that, and we're going to bring it back to ground. And then on D1, which is also an analog port A0, we're just going to hook a piece of bare wire to that. We're not even going to bring it to ground. And all we're going to do here, we're going to enable the touch sensor on this guy. And we want to have a big chunk of wire that we can touch rather than trying to fit our fingers in between all these pins and maybe shorting them out. So I have a nice bare wire here that we can touch and enable the touch sensor. And so here is the physical layout. So we have, I did this on a breadboard with a wire sticking out that I could touch, and then I built it on the circuit. So this design shows both the previous lab and this one. So this white LED over here is the new circuit, and all it is an LED like we built before, and then this chunk of bare wire that I put in there to touch. So it's a simplistic circuit. And then I have the strip board connection details here on the right if you're going to build that circuit. This set of examples that we're going to walk through is going to use the dot star RGB LED. So we're going to need to load some library files because these are not included in the CircuitPy file. So you're going to want to download the library bundle and extract it onto your PC. And then you're going to want to find these two files, Adafruit_.star and Adafruit_py pixel buff. We're going to copy those to the lib directory on the CircuitPy drive. All right, so here is our first piece of code. The very first piece of code, what we're going to do is blink the dot star RGB LED. So by blink, we're going to turn on red, green, blue, and then turn it off. So in that order. So we're actually flashing 3 colors and then turning it off. So the first thing that we do is import the library. So instead of having Adafruit underscore dot star, I'm renaming it dot star as I import it. So that's what this as does. And then I'm going to assign an object called dot using that dot star library. And this takes several parameters. So unlike a single LED, we have to give it several things. It wants to know a data pin. It wants to know a clock pin. It wants to know how many dots are in a chain, because you can chain dots together externally. And it wants to know the brightness that you want to display at. So I give it the values for the data pin, the clock pin. I tell it there's only one dot LED here. And I tell it a brightness of about 20%, because these things get very bright. You'll notice that the board references I'm using are not D7 and D8, which are listed on the pinout. And that's because the board definition library calls them out as these names instead. So then I'm going to run through my while loop. This is the main loop. And the first thing I'm going to do is I'm going to assign dot 0, and you'll notice it's presented as an array, because you can have more than one dot in a chain. It sets it up as like an array. So dot 0 is the dot that I'm working with. That's the first and only dot we have. And I'm going to make it equal to 25500, comma separated. So this is in Python called a list. I'm giving it a list of 3 values. The dot star is expecting that list to be in the format of red value, comma, green value, comma, blue value. And the values can be anywhere from 0 to 255. So 255 would be fully on, 0 would be fully off, and then red is obviously this value. So then I'm going to pause there, and then I'm going to do the same thing to set it to green, and then to blue, and then finally to off. And so we're going to loop through this, just blinking those LEDs, or that LED, those colors. Take a look at our next piece of code. So with this one, we're going to color cycle the onboard.star RGB LED. So we're going to take the dot star, and we're going to define it the same way we did before. So this top part of the code is the same. But now we're going to add a function. And we're going to call this function wheel. And I actually stole this function from the demo code that runs on the trinkets when you get a new trinket. So this wheel function is going to take in an integer, and it's going to use that integer, assuming it's between 0 and 255, because it's going to return a list, and it's going to return a list of all zeros if it's above 255 or below 0. And then it's going to do some math on the numbers to return the list in different ways based on that number. So I'm not going to get into the math here, but this is going to produce a very pretty wheel pattern as it goes through all the different colors. So I'm going to set an iteration number of I and set it to 0 before I go into my main loop. My main loop is going to be very simplistic. It's just going to set .0 to be equal to the function wheel, which I'm giving it I and 255 as the value to send into that wheel function. Now, I is the iteration number, right? So we have to iterate that. So I'm going to say I is equal to itself plus 1, and then I use a little math function here to make sure that it's not going to go over 255. So with this function, basically it's going to iterate between 0 and 255. If it hits what would normally be 256, it would go back down to 0. And then I'm going to sleep. And so it's going to run through that continuously. And that's how we work with functions, as well as how we can deal with different colors assignments on our RGB LED. All right, so next we're going to learn how to use a touch sensor. So for this, we're going to start with a simple LED code. And this is the LED that we wired up. We're going to add one library here called Touch.io, and this is a built-in library that is in addition to the digital I/O and the other stuff that we had. We're going to set our LED the way we normally would to a digital I/O port, but we're going to set an object called touch to a touch I/O port called touch in, and we're going to set that to an analog port, A0. Now, because this is an input port, we don't need to set direction on it, but we do need to tell it what direction the digital port for the LED is. And then the first thing we're going to do in our main loop is we're going to grab the value of the touch object. And then we're going to print that value. And then we're going to make a decision on that value. So if that value is greater than 3500 here, I'm going to assume that it was touched. And I'm going to light up the LED. Otherwise, the LED is going to stay blank. Now, you might ask where I got 3500. That's mainly trial and error, because as you build a circuit with capacitive touch, if you're bringing it into an analog input the way I am here, you're going to see values continuously because it's going to be receiving capacity or capacitive signals just from the air or from different things around it. And so it's never going to be a truly zero value. And you just have to look at what the values are that are ambient when you're not touching it, and what those values tend to jump above when you do touch it. And then that's how you choose the value to put into your conditional statement. In this case, I saw that most times the touch values were up over 4,000. So I chose 3,500, and the ambient values were someplace in the 2,000 range. And so now we're going to do that same thing, only with our dot star. So this one is going to be cool looking. If you actually take the lab, we'll go into what this looks like and work with it. But we're going to make sure that we import our dot star library as well as our touch.io library. And most of this is exactly the same as the code that we did to color cycle the dot star. The only real difference is I'm going to read in the touch value the same way I did in the previous example. I'll print that value. And then down when we're doing our dot star wheel, I'll go ahead and set the wheel and get a value for the dot star. I'm just going to make a decision on whether or not to increment the color or keep it the same. If the touch value is greater than 3,500, then I'll print that it's been touched, and I'll let that math to increment the I value work. And if not, it's never going to increment. So it will sit there at the same color until I touch the pin. And then when I'm touching or holding the pin, it will cycle through the colors. And when I let go, it'll stay at the color it's at. So it's kind of a cool little example of how to use touch in a loop like this. And that is the end of this presentation. I hope you enjoyed it. I hope you learned something from it. And I hope to see you in the lab presentations, where those labs 4 and 5, I'll go into much greater detail in those separate videos. This slide deck is available at altbeer.us/CircuitPython. And then all of the code is available on GitHub and will be linked in. Thank you so much.